Hello, welcome to tutorial number 13 of the AOU course Introduction to Linear Algebra. In this tutorial we will talk about section 4.2, and this section 4.2 is part of the chapter 4, which is about linear transformation, null spaces and ranges. In this section specifically we will talk about the null space and the range. What are the definition of the null space? How do we find them? What is the definition of range? And how do we find it? Let's look at the definitions first. Looking at the null space and range, let V and W be vector spaces. For a linear transformation T from V to W, the null space of T designated by NT is defined by NT is equal to all vectors X that belong to V such that the transformation of X is equal to 0 in W. Therefore, NT is the set of vectors when transformed produce the vector 0. The range of T, which is designated by RT, is defined by RT is equal to the transformation of X such that X belongs to V. The sketches here below on the left and right are a clear representation of the NT and RT. If you notice here on the left side, we have the two vector spaces V and W. We have the transformation from V to W, and we have NT as defined here. NT is a set that belongs to the vector space V. When transformed, it produces 0. Therefore, we can safely say that the null space NT is a subspace of the vector space V. Similarly here, RT is a vector. If we take the transformation from V to W, RT is the range of T. The range of T is a subspace of or a subset of W, the vector space W, as can be seen here. Let's look at some examples related to the null space and the range and how we can find them. For the null space, let's define the linear transformation T from R3 to R2 by transformation of any vector in R3 is equal to X minus Z, Y plus Z. It is clear that the transformation on the right hand side belongs to R2. Find the null space NT. So the question is to find the null space NT. In order to answer this question, the best thing is to apply the definition. Definition is, as can be seen, the null space is a vector in R3 in this case, such that when transformed creates or provides an output of 0, the 0 vector. In this case, transformation X, Y, Z equal to 0. Therefore, we set the output here in R2 equal to 0, which is similarly to solving a system of two equations and 3 unknowns. In this case, we can create the augmented matrix or solve it directly here. It's obvious that the solution of this homogeneous equation is as follows: Z is equal to T, Y equal to minus T, and X is equal to T. Therefore, the NT, the null space of T, is equal to T minus T such that T belongs to R. Let's look at the range of T. An example about the range. Define the linear transformation, same linear transformation that we've seen before in the previous example, where T, the transformation of any vector X, Y, Z to R2 produces X minus Z, Y plus Z, which is again in R2. The question is to find the range RT. As we know, the range is a subset on the right hand side in R2, is a subset in R2. Again, we apply the definition. Therefore, the range of T is the following subspace of R2. RT is equal to the transformation of the vectors, coordinate vectors, E1, E2, and E3, which creates the span again in R2 corresponding to E1, E2, and the vector minus 1, 1. Okay, therefore, if we find the basis for the span, it is obvious that the basis are the first two vectors, since this can be written as a linear combination of these two. Therefore, RT is the span of these two vectors, and RT is equal to xy, such that x and y belongs to R. Another example, example number 3. Let T be a transformation from R3 to R3, a linear transformation. Again, this is called a linear operator, since we are moving or doing the transformation within the same vector space. And this transformation is defined as follows. We take any vector in R3, and the output is x plus y plus z. We need to find the null space of T and the range of T. Again, we apply the definitions. With respect to the null space is found by transforming the vector, and the transformation results in the zero vector. So we set the output, the right hand side, equal to 0, and we solve. Doing that, we notice that in this case x equal to y equal to z equal to 0. Therefore, nt is equal to the 0 vector. On the other hand, rt in this case is obviously equal to the span of the transformation of 1, 0, 0, 0, 1, 0, and 0, 0, 1, which is the same as the span of 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, which is equal to R3. So RT is the range of T is a set that can be created by a linear combination of these vectors. As a conclusion, and to summarize our findings, if T is a linear transformation from Rn to Rm, then the null space Nt is a subspace of Rn. We've talked about this before. The range Rt is a subspace of Rm, this side, the right hand side. Also, dimension of Nt plus dimension of Rt is equal to n. Let A be an m by n matrix. The rank of A is the number of leading ones in the reduced row echelon form of A. Also, the rank of A plus nullity of A is equal to n. An n by n matrix A is non-singular if and only if rank A equal to n and nullity of A is equal to 0. This concludes our discussion for section 4.2 of chapter 4. Good luck.